Recording is rolling. It is Thursday, October 24th. I do want to start universal gravitation with you guys by the end of class today, but I'm going to build up to actually, we're going to do some review questions first and also hit some review videos. I got some review video demos for you guys, right? And then have a O'Neill cylinder question here pretty soon, right? But before we get to this O'Neill cylinder question, let me build up to that. So I'm going to switch my screen over. I'm going to go back a while ago. Got some video demos. Now, my sound's not working right now. I need to figure out why later. But so the only ones I can really show you guys, the ones where I can just narrate it myself. I think this is going to be all right here. All right, here we go. All right, so let's go way back. This is a video demo I always meant to show you guys. I just never fit it in, right? This guy is standing on a scale inside an elevator. Now, right now, the elevator's at rest. It hasn't started moving yet. Guys, how much does that guy weigh? About 200 pounds, about? You guys see 200 pounds? Right. Let's see. Elevator doors close. And what's going to happen next? Oh, look at that. You guys see the needle shoot up to about 220? That's probably pounds, right? Like 220 pounds, right? Ooh. Now, guys, if the needle moved up, which way does that tell you is the elevator accelerating? Upward, right? Has to be going upward, right? All right. Which, therefore, if it started from rest, it must also be moving which way? Upward, right? Because if it started from rest and accelerates upward, that means it's also moving upward, right? Right. So get that. Hey, the fact that did his weight or I should say the normal force, right? Guys, if I had you draw a free body diagram on this guy, he has a weight down and a normal force acting up. Is that true? And that scale is really telling you the normal force. What is the normal force on that guy? Okay. You guys see how the normal force is about 10% larger than his actual weight, going from 200 to 220? That's an increase of about 10%, isn't it? Do you think you could calculate what is the upward acceleration of that elevator? Do you think it's about 10% of the gravity field? Guys, what is 10% of Earth's gravity field approximately equal to? 1 meter per second squared, right? I bet I could formally write that out on paper, but I bet that's about what it is, right? All right, let's see what else, because he's not going to accelerate up forever. So what's going to happen next? All right. Okay, so eventually it goes back to level, right? So back to 200 pounds, let's call it. Right. Guys, does that mean is the elevator probably going up at constant speed at this point? Constant speed, okay? And then what? Right. Then it dips down to, well, let's just round that down to about 180, right? So it looks like he lost about 10% of his weight. Well, his weight didn't change, but the normal force rating went down by about 10%, right? Right. Does that mean at that point the elevator is slowing to a stop? Yeah, because it's accelerating down. That could be slowing to a stop while it's moving upward. So guys, that entire video, the elevator was always moving upward. But it started accelerating upward, and now at that snapshot right there where I've got paused, it's accelerating downward. Slowing to stop. Got that. Yeah. Here's another one I meant to fit in a few weeks ago. It's the slinky drop. Slinky drop. So let me zoom to, right. This guy's going to drop a slinky. I wonder what's going to happen. Oh, it falls. Great. But what does that look like in slow motion? In slow motion. All right, you guys ready for this? This is wacky. All right, slow motion time. Whoa, 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 whoa. All right, so let's rewind. Let's make sense of this. So he drops that slinky. Now if he just dropped the ball would just free fall down, right? But the slinky, right? It's a little funny looking story, right? Hey, look at the bottom of the slinky. It's just staying in place, right? So if I pause it right there, suppose you make a free body diagram of a mass point near the bottom of the slinky. Maybe break up the slinky into like 1,000 little parts, right? We're looking at one part right near the bottom of the slinky, right? Guys, what are the forces acting on a mass point at the bottom of the slinky? Yeah, its weight's pulling down, but it's not falling down. What's holding it in check? A tension force. Isn't there a tension in the slinky that's pulling it up, right? So you got the weight down, you got the tension up, and it's a wash. It's in balance. That's why it's just floating it. Right now, eventually it falls, but it takes some time. There's a time lag before the information about the drop can reach the bottom of the slinky, right? Oh, let's go back. Let's do some more questions. How about there's a lot of ways I can go with this. Right? How about this? That guys, that slinky right there. Could that be kind of like a spring with a tiny, tiny, tiny spring constant? Isn't that what a slinky is? Right? You put a little force and it stretches really easy. That's like a spring with a tiny spring constant. Right? Turns out all physical materials are effectively some form of a spring. So, like, even if I'm writing with an ink pen, it's like a very, very stiff spring. And what that means, from this video, what you can gather is like if I'm writing with a pen or I drop a pen or I move one end of a pen, the information does not immediately reach the other end of the pen. It actually takes some time for that information to propagate through. That's how fast does a wave travel through any material? It travels at the speed of sound, right? The speed of sound. That's how fast that's what sound is. It's a wave propagating through some material, right? Oh, what's the limiting speed in the universe? Nothing can travel faster than light. Yeah, light, the speed of light, right? Um, there are thought experiments people come up with. Well, what if I do this? What if I do this? And they all fail for certain reasons. That we'll talk about theory of relativity, why you can never break the speed of light, right? But um, you can never travel through space faster than the speed of light, I should say, right? But here's one idea people have. Hey, what if you had a really, really long rod and it went from the Earth all the way to the moon and you swing it like a baseball bat? Wouldn't the end of that rod travel faster than the speed of light? Because on paper, it sure looks like it would, right? But that long rod is kind of like the slinky in a sense. It's just very stiff spring and it actually takes a long time for that wave to propagate through. And no part will ever actually travel faster than the speed of light. That's what's going to happen. Right. How about this? Let's look at the top of the slinky. So here, let's say right about there. Okay. Guys, what are the forces on a top part of the slinky? What are the two forces? Yeah, the weight pulls down. Is there any other force acting on the top of the slinky? The tension, which pulls which way? Also down. Hey, the bottom of the slinky was opposite. It was weight down and tension up, and it was the wash. The top of the slinky, I think it's weight down, tension down. Ooh, great. Do you guys think uh yeah, that's like G forces. So that's gonna lead into this question. What if at the exact same time he's dropping the slinky, right there, right there. You guys see he's just letting go of the top of the slinky? What if at the same time he reaches out and he drops a baseball from the same height? And you watch the baseball next to the top of the slinky. Let's go forward a little bit. Right. Now, right here, at that snapshot right there, supposing you dropped a baseball, would that baseball be level with the top of the slinky? Or would that baseball be like probably down here, like falling faster than the top of the slinky? Or would that baseball be about here, falling slower than the top of the slinky? What do you guys think? Show hands. How many guys think the baseball would be level with the top of the slinky? Right. How many guys think the baseball would be accelerating faster and be like way down here? Who thinks the baseball would be here accelerating but not as fast as the top of the slinky? Yeah, I agree with you. I think the baseball would be probably right about where my mouse cursor is right here. Right? Because the baseball is only under the influence of its own weight. Divided by its mass, it's accelerating at pure 9.8 meter per second squared. Right? But the top of the slinky, that has its weight, but also the additional tension force. So it's going to accelerate faster than free fall. Okay. Now, what about the slinky as a whole? Does the slinky as a whole have a center of mass right about here at that snapshot? Now, it turns out the center of mass is in pure free fall, 9.8 meters per second squared, right? But that slinky is like collapsing. So the bottom's not moving at all. The center mass is pure free fall, and the top is accelerating probably double G, probably like about 20 meters per second squared. Okay, let's get that. All right, so a lot of fun things with that one. That's a good one. Okay. But I'm about to ask you guys a question about an O'Neill cylinder, which we talked about a little bit last couple of days. Give you guys a visual. Do you guys know what movie this is from? Huh? It's from a movie called 2001: Space Odyssey. Oh yeah. Okay. This was made back in the 1960s, and you can kind of tell because the scene goes on for well, like over 30 seconds. Yeah, everything was slower paced back then. That's part of the fun of 1960s movies. There you go. But that's kind of what that would look like, right? If you had a giant wheel in space, and what if you were walking around on the inside? Would that feel like an artificial gravity field? Like you could walk around on the floor on the inside? Let's go inside. I wonder what that would look like on the inside. I think this is supposed to be a different one, but same idea. It would look kind of like this. Right, where no matter where you're standing on the floor, like you always think like towards the outside of the circle is down. That's what you would feel like if you were blindfolded. Is that true? Right. And again, this guy isn't really. This is all just a movie, right? This is special effects. I think what they actually did is they created a giant hamster wheel. They rotated it. They had the camera fixed at one point, and that guy's always just running on Earth. He's on Earth, really, right? Okay. But this is kind of what it would look like. Okay. Now, truth be told, if you actually made like an exact one-on-one scale model of this in space, it would be kind of too small. And I'll show you guys why. Because I have a real one. All right, let's look at all right. Do you guys know this YouTube channel, Tom Scott? All right. So one video, he goes inside a rotating room. Oh, there it is. Right, you guys can see that room rotating. See, there's another shot of it somewhere near the beginning. I always have trouble finding exactly. Well, anyway, he's in a rotating room. You guys get that? He's in a rotating room, right? Now, in a rotating room, it's okay. Rotating frame of reference. Oh, there it is. That's what I was looking for. Okay, you guys saw that room rotating. Basically a merry-go-round, but it has walls, so you can't see the outside world. So maybe kind of having a blindfold on. All you see is the room. That's your frame of reference, but it's a rotating frame of reference. And this room gets really wonky. It's really weird. So here's one thing I wanted to point out. See how he's leaning forward. But if he was blindfolded or closed his eyes, he would feel like he was standing straight up. But you guys see him leaning forward, right? Because of these rotational mechanics, right? Like centripetal force and the whole effect, right? Right. What else we got here? Right. One thing you'll notice is that these people in the room, they're making a special effort to keep their heads really, really still. See how they're not moving their heads? Right? Like right now, if you close your eyes, you know you're sitting right side up. And if you lie down and still have your eyes closed, you know you're lying down. Guys, how does your brain know your orientation, whether you're right side up or lying down? Your inner ear. Exactly. You got some fluid in your inner ear. You guys ever like spin around, get really dizzy, and then you can't walk straight for like a minute, right? Because that fluid in your inner ear is all like sloshed around, and that's what tells your brain like which way is up. Okay? So right now they're told make sure you keep your head really, really still, because if you move your head, your brain gets all wacky and doesn't know which way is which, and you're just gonna fall over and get all dizzy, right? So right now he's acclimating himself, just like moving his arms around, so he's getting used to that rotating environment. Because he's trying to swing his arms straight at first, but they would go to the side. It's like, what? Move forward and goes to the side. All right, here, he's going to throw a ball. Throw his tennis ball. Now, if you were above, looking straight down, think that tennis ball would look like it was going just forward in a straight line? Yeah, that's the law of inertia. It's first law. But inside that rotating frame of reference, it looks like it's curving off to the side. What effect is that called again? Coriolis. Coriolis. Yeah, you guys remember Coriolis effect? Let's see that again. Throw that ball. Now he's got to throw it to the side so that so you can actually catch it. There you go. Rotating forward. All right. So that's all videos I've been wanting to show you guys. So fill in some blanks there. Right. Let's go back to this. Right, so we're back to the O'Neill cylinder. You guys see O'Neill cylinder? Right. And I got some questions about this. Let's do trying to get used to my new system here. I think if I slide this over here. Okay. You guys see that? The camera's seeing that. Okay. I think we're back. All right. So we got this. I got this O'Neill cylinder. I'll remind you guys a little bit where the mathematics come from, so you can actually solve this mathematically. All right. You guys did this lab recently. You guys remember this lab? And this is what we came up with. The centripetal force, in this case provided by the tension, is equal to mv squared over r. You guys remember that? This m, this v squared divided by this r. Boom. Okay. The lab before that, you guys had a turntable, and we had determined this, that a tangential speed, like a linear speed, is equal to the angular speed. That's this omega in radians per second. The whole turntable's turned the same omega everywhere. Okay. Right. But then if you want the linear speed, say for like, I put a coin right there, just take that angular speed and multiply by its radial distance from the center. You guys remember that? Right. All right. Then I can do a substitution. I can take this idea and this idea, and I can put the two ideas together, and it looks like this. Here's V equals omega r. Here's mv squared over r for centripetal force. Substitute right there. Do a few steps, and it looks like this. Centripetal force, now for like a rigid rotating turntable or O'Neill cylinder you're about to do, is m omega squared times r. So this is centripetal force, not as a function of linear speed, but as a function of angular speed. So the whole disk is rotating. You guys see that? Right, so we got that. Right. And now you can answer these questions here. So what's the question? Suppose you got an O'Neill cylinder. Oh, I made up a number this morning. I said, let's call the radius 500 meters. You guys got that? Radius is 500 meters. Maybe I should have said that. Here, I'll ask you guys a side question. What is the diameter equal to? 1,000 meters. That would be exactly 1 kilometer. Maybe I should have said that, right? But I went ahead and gave you guys the radius is 500 meters, which fits nicely into the equation, right? And now, if it's not spinning at all, then what would it feel like on the inside? Well, if it's not spinning, nothing's but you'd just be floating around. This is out in deep space, right? You guys got that? It's out in deep space. You just be floating around like an astronaut, right? Now we're going to give it a rotation. You see, I have a central axis right here. It dashed off the central axis. Okay? I've got this omega right here, and it's going to spin. Now, the faster you spin it, do you think that these people walking around on the inside feel heavier, heavier, heavier? They do. What do you think would be a good target artificial gravity for them to be walking around in? What number should we be aiming for? 10 meters per second squared, right? Because Earth gravity, that would be a good value, right? I put 9.8. Okay, so that's what I got on this paper. Let's go 9.8 meters per second squared, right? Give it a spin, right? That's the artificial gravity. Now, there's no real gravity fields anywhere nearby, but we can simulate this, right? By spinning it at a certain angular velocity. And that's my first question. How fast do you have to rotate that whole O'Neill cylinder about that central axis so that everybody walking around on the inside experiences, 9.8 meters per second squared? How fast do I have to rotate? Right. Give you guys a minute to solve that. Oh, put you guys out a little bit. You guys know you can use a formula off this page. You guys know this poster is hanging from my ceiling right there too, right? So you guys can reference it there. So you guys know all that. All right. Does anybody know by now how fast it has to rotate? Here. Give you guys a little more help. Right. So if we're talking about an artificial gravity field, am I talking about a force or an acceleration? What am I talking about? An acceleration, right? Okay. Like all these people walking around, they might be different masses. May have small people, tall people, whatever, different masses, right? But they all experience the same gravity field. That'd be true for artificial gravity. Okay. So take gravity force, divide by mass, you get the centripetal acceleration, which is same for all of them. Right. Okay. You guys said what number should go right here for acceleration? 9.8 meters per second squared. Okay. Did I tell you guys the radial size? Okay. What does omega mean? Angular velocity. Right? Like how fast is it rotating? Put that all together. How about now? Who knows? Yeah, what you guys say?
0.14.
Aha! All right. So 0.14, and what units would that be? 0.14 what?
Radians per second.
Radians per second. Exactly. 0.14 radians per second. All right. So go over this with you guys. So you guys started with this formula. Centripetal acceleration is omega squared times r. Okay. So here's how fast it's rotating. You're solving for that. Okay. Now I solved this two different ways. I solved in terms of variables and I solved in terms of numbers. So I'm going to split my paper, do it two different ways. Okay. So I'll start with the formula. Centripetal acceleration is omega squared times r. Right? If I plug in the numbers first, here's my target acceleration, 9.8 meters per second squared. Here's the radius, is 500 meters. Right? And I'm solving for this omega. Right? Guys, what's the next algebra step? Divide both sides by 500? Or wait, yeah. That's, so divide both sides by 500 meters. Right? Or in terms of variables, whatever the radius is, just divide that over. Right? What's the next algebra step? Square root. Aha, square root. And if you take that square root, the number you get is 0.14, and the units are going to naturally be radians per second. Because remember, if you anything to do with angles, if you're plugging directly formulas with no sine or cosine, anything like that, you naturally get radians for angle and radians per second for angular velocity. Just like that. All right, guys good? I got a follow-up question. I actually got a few follow-up questions. How many degrees per second is that? Because radians per second, I don't know if you guys ever worked with radians in the past, maybe, right? But degrees, oh, you guys have a protractor with degrees. I bet it's probably easier to imagine how many degrees something is, right? And per second, okay, so this thing is rotating at some angular speed. Okay. How many degrees per second is that equal to? How many degrees per second? Kudos. I guess something small, I think. Huh? Okay. Okay. Let's do a conversion. We'll do a unit conversion here. All right, so everybody knows angular velocity is 0.14 radians per second. You guys got that, right? All right, so you guys got that written down. All right. Now, let's take, well, here, okay, I guess, here, I'll show you guys two different ways to do this. Right. I should have asked you, because this would have helped you out a lot, is how do you relate degrees to radians and revolutions? There's three different ways to measure how far something's turned. Right? So let's start with one revolution. Guys, one revolution is how many degrees? 360 degrees, which is how many radians? 2 pi radians. So 2 pi radians is equivalent to 360 degrees. Isn't that true? Right. Or I've seen a lot of students do this too. 180 divided by pi. You could just do that. That's also the same ratio. Right. Let me do this with you guys. Guys, pick up a calculator. We're going to do a check here. Make sure you can type this correctly. So 0.14 radians per second times 360 degrees divided by 2 pi radians. And I should get 8 degrees per second. Isn't that true? 8 degrees per second. Can you guys imagine that? Turning 8 degrees per second? Probably something about this. Maybe pretty close to that video. Let's see. Am I going to get 8? Oh, no. I got 79. I must have typed something wrong. I'm saying this because I've seen students do this even to this point in the class. Okay, guys, how did I type that wrong? What did I do wrong on my calculator? Guys, it has to do with this 2 pi. You guys see it did divide by 2 pi. You guys see that? Right. How did I type the 2 pi wrong? Parentheses. I need some parentheses. How's calculators interpreting this? And again, I've seen students do this like even recently. I think right that's why I'm showing you guys this right now. I'm making such a big point about this. Is the calculator divides by 2 and then it turns around and multiplies by pi? No, that's not what I want. I want the 2 pi to all be in the denominator. So here I can fix that. Scroll up, scroll over, and then second insert a parenthesis right here and group that together. Now my 2 pi is in parentheses. You guys see that? Okay, now we're good. 8.0 degrees per second. You guys see 8 degrees per second? Okay. How about this? Does anybody remember how many degrees are in 1 radian? It's about 57, not exactly. I think it's 57 point something, right? But you can round a little bit. I think it's 57.3, something like that. Right. Let's do 0.14 radians per second times 57 degrees in a radian. Oh, look, it's the same thing. It's still 8 degrees per second. Is that true? Okay. So there's 2 different ways to do that. All right, is that okay? Right. So naturally, mathematically, you get radians per second. But maybe if it's more intuitive to get degrees per second, you could still do that conversion. Right? You guys still know how to do unit conversion in this class. Right? You just break out some railroad tracks just like you did there. Okay. I got another question. Guys, if it's rotating this fast, then how much time does it take to complete 1 revolution? Go ahead, give you guys a minute to solve that. How much time does it take to complete 1 revolution? Right, okay, that's this question right here. How much time for one revolution? Okay. Everybody knows how fast it's spinning? 0.114, 0.14 radians per second. How much time to go around once? All right, who knows? Who knows? All right. Here, uh, here's one way to do this. You guys remember way back in the day, distance equals speed times time? You guys remember that? Or maybe you knew that before you ever set foot in this class. Okay. Now, what's the turntable version of that formula? Like for guys, for a turntable, what's an equivalent expression? Boom, that right there. Here's angular displacement. How far does it turn in radians? Here's angular velocity. How fast is it spinning in radians per second? And then time. It's the same thing. It's still distance equals speed times time, but now it's the turntable version, right? In radians. Okay. Right. All right. Now, you know some of these values. Because if I say one revolution, say one complete rotation, what could you plug in for this theta right here? Huh? What? I give you some options. You can call it 2 pi radians. You could also call it 360 degrees. Right? Is that true? One revolution. Right? And then how fast is it spinning? Well, we did 2 versions of that also. You got 0.14 radians per second. Or did we also say that was equal to about 8 degrees per second? So either way. And then you can solve for time. So it's still multiplied by time, isn't it? Right. Go ahead before I reveal the rest of that page. Somebody tell me, how much time does it take to rotate once? 45 seconds? About 45 seconds? Yeah. Not exactly. It's like a decimal, but it's about 45 seconds. There you go. Right. So takeaway is, if someday, maybe, I don't know, 200 years from now, we're building this exactly up in space, a 500-meter radius O'Neill cylinder. You say, well, we want to spin this. How fast should I spin it? Or how much time should it take to go around once? If you time it, and it's taking about 45 seconds for this O'Neill cylinder to go around once, then that's probably the optimal angular velocity, because that would result in an artificial acceleration that would, a centripetal acceleration that would match Earth's gravity field. All right. All right, let's flip over to PowerPoint. It's going to be PowerPoint time. PowerPoint. I think, yeah. I think I hit all my demos. Good. All right, so we're going to do a little bit of review, and then we're going to get on to new stuff. All right, so going back a ways, this is a recent lab you guys did. You guys remember centripetal force lab? You guys fill out this table. Then we put together, as a class, these 7 different graphs. Now, you individually could put together maybe 2 or 3 of those, but all together, we put together all 7. You guys remember that? That's your last lab. That's back in your return folder. You guys got those? All right, then, okay, and this is the master equation we came up with. Centripetal force is mv squared over r, or centripetal acceleration is just v squared over r. You guys got that? Okay. Then we combine that with turntable physics and say, well, if you substitute in omega times r for that v, you can come up with maybe something that's more applicable to a turntable or O'Neill cylinder. Now, centripetal force is m omega squared times r, or centripetal acceleration just plain omega squared times r, right? For the whole turntable. You guys got it? Here's how this could be more helpful for a rigid disk, right? You guys see this guy climbing this ladder? Climbing the ladder, getting up towards the center, right? Well, every rung of the ladder is moving at a different linear speed, but the same angular speed. Like if you're floating in a space station out here, and you point a radar gun at every rung of the ladder, it's going to show a different linear speed. So if you try to apply this formula, I mean, I guess you could, it'd just be really, really messy. Okay. But if you have this formula right here with the omega in it, okay, then every single point on this O'Neill cylinder has the same angular velocity. So it's really easy. So, well, what is the radial distance? Right. Guys, what is this guy climbs to this? Do you guys see this dashed off central axis that it's actually rotating about? Right. What if he climbs right to the center of the ladder? So he's right on that axis. What does he feel like? Weightless. He feels weightless. Because you can follow the formulas too. If you're zero distance from the center, multiply by zero, you get zero effect. Yeah, so you can push off, just like float into space. So like that. All right, so put him down here. He's gonna climb down the ladder. Just walk around this ground. Okay. All right. Okay. This one you haven't seen yet. I'd like to do this lab soon, maybe next week if I can fit it in. I don't know. We'll see. But turntable friction. At some point, I want to break out the turntables again and have you guys put a coin on the turntable, give it a spin. Now, guys, if you spin it kind of slow, the coin probably going to stay on the surface, right? It's all good. Just spin a little faster, a little faster, a little faster. At some point, isn't that coin going to break friction and slide off? Right? Now, if you know how fast you're rotating it at the point that it breaks friction and slide off, you can calculate the coefficient of static friction. And here's the whole proof of how to do that. So here, I want to just plant that idea today, and we might come back to that in the near future, hopefully, I think. Right? Give you guys a lab table. You guys do that. Right? Now, this one I showed you guys remember at this point, there's 3 different kind of accelerations. So let's do a quick recap. You got your tangential linear type acceleration. How fast are you speeding up or slowing down? That could be in meters per second squared. That's this green one. Then there's this angular acceleration alpha. That's for a whole turntable. That could be in radians per second. How fast is a whole turntable rotating? Right? Or O'Neill cylinder for that matter, rotating. Right? And then the last one you guys learned, the most recent one you guys learned is the centripetal acceleration. So that's back to meters per second squared. Right? But it's always directed towards the center of the curve, right? Towards the center of the circle, right? Because if you're on a curved path, there's some force that's forcing you to stay on a curved path. Divide by your own mass, you get the resulting centripetal acceleration. That, right? All right. Conical pendulum. All right. So if you slow down your last lab, might look more like a cone shape. You might consider this is actually 3 dimensions. So 2 forces on this mass out here. A weight down, tension force up to the left. You can break that tension into components. I have some equations here. You could do a system of equations. There's lots of questions you could ask about this. And then this would always be the starting point. Got that? Okay. This one, vertical loop. We're looking at a couple of scenarios with this one. You guys remember the water in the cup? Right, so water in a cup, vertical circle. What's the minimum speed to get around the top? Right, so here's the general solution to that. Right, or you could swap out that with the story of going through a vertical loop in a roller coaster. And it's the same math, and it's the same story. Okay, the story of vertical loop. Okay. Ooh, Ferris wheel and ball and string. You guys have not seen this one yet. This one I mostly made for my AP students, but maybe I'll do it really fast with you guys, because AP likes to ask questions off this page. Right? Suppose you have a ball on a string. Picture on the right, ball on a string. What are the forces on the ball at any point going around the vertical circle? And it is a vertical circle, right? It's going up, down, up, down, up, down. Right? So do you think the weight of the ball is always pulling down? Yeah. Do you think the tension of the string always pulls in the direction of the string? Yep. And that's exactly what I've shown here. Right? So you got that. Let's say that one side. Let's go to the Ferris wheel. Now, the Ferris wheel is a different type scenario because the Ferris wheel is now a rigid circle. It's like kind of like the turntable, kind of like the O'Neill cylinder. Maybe it's easier to think of this in terms of omega, constant angular velocity. Every single one of these booths could have the same speed. Every single one. That's not necessarily true with the ball and the string. Back to the ball and the string. Do you guys think that the ball is probably speeding up on the way down and slowing down on the way up because gravity's pulling down? Right? So I bet the speed of the ball is always changing. But the Ferris wheel boosts, I bet they're always going like the same speed as it goes around. Okay, so it's a little bit different. Right? Because what if you're sitting on a scale and you're going around the top and you're whizzing around pretty fast? They got the spinning pretty fast, this Ferris wheel. It's going zoom, zoom, zoom. Right? Because at the top, do you feel a little bit light or a little bit heavy? A little bit light. At the bottom, you feel a little bit what? A little bit heavy. See, the normal force is more than the weight at the bottom. Okay. That's related to this one here. Suppose you're in a car going over a hill and then through a valley. So you're going pretty fast. Zoom. So the car is always going forward, so left to right. Right? Free body diagram. This car has the same weight everywhere, mg, that's the same, right? But if you're inside the car, you might not feel that. Guys, going over the hill, you feel a little bit what? A little bit lighter, a little bit heavy, a little bit light, right? If you're sitting on a scale, that same story. The normal force is less than the weight, right? In fact, guys, if I do this, if I get weight minus normal force, you guys get that? So I'm looking at the hill, weight minus normal force. That's called the what kind of force? This weight minus this normal is called the net force, right? The net force, as in like the net effect, as if there was a single force. And it would be downwards because the weight's more than the normal force, right? That net force is also acting as the what kind of force? Starts with a C. Centripetal, because isn't this car on a curved path? Right? It's a vertical curved path. Okay. Now, how about the valley? Can I do this normal force minus this weight? And that would be the net force over there, which would be acting as the centripetal force. You could apply the equation, mv squared over r. Normal force minus weight is equal to mv squared over r. Look at that. The faster the car goes, the greater the difference. All right, car turns on a bank track. I think you guys saw this one, right? We talked about this one a little bit. So let's get past. I drive that with you guys. All right, now we're ready for new stuff. It's new stuff time. Yeah, here, just make it a little bit dramatic. Maybe you get the lights off because we'll be talking about space. So I put this kind of historically chronological. So I got Kepler up here first, but I'm gonna build towards. I'm gonna get universal gravitation in class before the end of class today. Okay, so let's go way back in time. Let's go back. About 2,000 years ago, guys. 2,000 years ago, talk to some random person on the street. Say, hey, what's at the center of the solar system, center of the universe? What would people say 2,000 years ago? Yeah, the Earth. They thought the Earth was. Now, you guys know that's not the case, right? Because which scientist came along? His name starts with a C. He says, actually, I think the sun's at the center. Who was that? Copernicus. Yeah, guys remember Copernicus, right? So, yeah, because watching the very carefully the motions of everything in the sky, especially planets like the planet Mars. Now, most things in the sky, like the moon, okay, it's going around, great. Now the sun appears to be going around the Earth, there's because of relative motion and the Earth is spinning. Right? We know that nowadays. People didn't know that back then, right? But if you look at planets like Mars, you see something weird, which is it looks like the planet like Mars is moving one way across the sky, and then it appears to have some weird retrograde motion and goes back the other way. And then it turns back the way it was originally going and moves on. Okay. Now, people knew that, but they thought, okay, well, maybe there's some kind of spiral physics that we don't understand that's causing it to do that. We don't know why. Okay. But Copernicus said, wait a minute. I think what's actually going on is that the Earth is not at the center. I'm going to put the sun at the center. That's called a heliocentric model. Heliocentric, sun center model. Heliocentric model. The sun's at the center. And I think all the planets, including the Earth, are going around that. All right. This is when astronomy and astrology kind of start to diverge. Right? Guys, what's the difference between astronomy and astrology? Yeah. Guys, if you ever hear like what's your sign, man? You a Capricorn, right? You hear some of that? That's astrology, right? Like looking at constellations and signs and saying like, what does that mean about my personality? That's astrology. Okay. Now, in astronomy is saying, well, where is the star night by night location exactly in the sky? How many degrees above the horizon? And like, how do the galaxies form? And what's the life cycle of a star? That's astronomy, right? Now, back 2,000 years ago, it was all sort of the same thing. People would just look at the sky saying, how do we interpret this? What does this all mean? Right. And by the time you get to modern day, now it's split off into two completely different things. Right. So astronomy. All right. So, okay. So Copernicus come and gone by this point. We're about to bring in Kepler. Now, Kepler actually precedes Isaac Newton. So what you guys are looking at right now, this is all before Isaac Newton even comes along with universal gravitation. People don't even understand. People don't know the laws of motion at this point, right? What they do know is they have this big old book of astronomical data. Kepler got it from a guy named Tycho Brahe. And what Tycho Brahe did, like night after night for many years, is he would track extremely precisely in the sky where are all these different objects, like the planet Mars, for example. And you say, okay, we'll see, it's 6:30 at night, and it looks like Mars is 31.85 degrees above the horizon. They do this like every night, like for years. Okay? I don't even know how he got these crazy precise values they did. It's like we're talking about like a fraction of a degree above the horizon, like level of precision they had to get for Kepler to be able to interpret this data and come up with these laws of planetary motion. And Kepler, like after like so many years of crunching this data, comes up with these 3 laws about how planets move. Says, okay, I think I figured this out, how things move. All right, first law of motion is that planets don't actually move in circles, they move in ellipses. Now, the orbits are pretty close to circles, but they are not exactly circles. Okay? And that actually makes sense because a circle is actually not super stable. If you're going in a circle and you went any slower, you would eventually spiral into the sun. So ellipse is a little bit more stable, right? So they're like slight ellipses. And for that matter, did you guys learn about ellipses in maybe Algebra 2 class? Maybe, right? Got a couple of focal points for an ellipse. I want to do an activity with this with you guys, but I'm going to save this for a different day. Maybe tomorrow. I'll have you guys draw an ellipse, right? Like a true, pure ellipse, right? And anyway, there could be these 2 focal points when we eventually do this activity. It turns out the sun is at one of those focal points. Okay, we've got the planet going around. Okay, so we got that, right? Right now, guys, as the planet's going around the sun, because the orbit is slightly elliptical, do you think its speed changes a little bit as it's going around? A little faster, a little slower, a little faster, a little slower? Okay. Where do you think it's going a little bit faster? Is it going faster at this aphelion far away from the sun or this perihelion close to the sun? Where's it going a little faster? The perihelion, when it's close to the sun, swinging around here pretty fast, right? Versus when it gets to the far side, the aphelion, it's going a little bit slower. Okay, a little slower here, a little faster here, great. And this leads to the second law of planetary motion that Kepler covered. It said, hey, if you look at how much time it takes for a planet to move, let's call this, I don't know, 30 days. It takes 30 days to go from here to here. It takes 30 days to go from here to here. And you make a wedge with the sun. You guys see this green wedge? You color that in. You color that in. And you compare those 2 wedges. As which wedge is bigger? This wedge, the skinny wedge on the right, or this fat wedge on the left? They're the same. Equal areas and equal time intervals. Equal. Yeah. So that's the second law of planetary motion. Equal areas and equal time intervals, right? Many years after that, he came up with this third law of planetary motion. It says, hey, now this one says, see, time period squared is proportional to the distance cubed. R could be a radial distance, right? Hey, maybe like a radius of orbit. He says, if you look at the time it takes for a planet to go around the sun, and you square that, which, by the way, what would that be for the Earth? If you want to plug in for the Earth, how much time does it take to go around? What would you plug in? 365 days could be, right? So this could be 365 days for the Earth. And you say, well, how far away is the Earth from the sun? I think it's like 150 million kilometers, I think. And you cube that number. And you look at the ratio of those. Suppose you do t cubed divided by r cubed. Sorry, t squared divided by r cubed. That's what I meant to say. T squared divided by r cubed, right? You come up with some number, right? Some ratio. And then you look at all the other planets. Turns out every single planet in our solar system has that same ratio, t squared over r cubed. Now, if you look at a different solar system, it's going to be different because different stars have different masses. But anything orbiting the same thing, in this case, the sun, is going to have the same ratio, t squared over r cubed. Right? So, right. Now, here's this last cell on the bottom right. This is an exact equation. This is the updated version of this after you bring in Newtonian mechanics. Remember, at this point, like Kepler precedes Isaac Newton, comes before Isaac Newton, right? When we bring in universal gravity, now we can make an exact equation with this. Oh, you know what else I meant to mention? This R is kind of an average value because remember, it's not true circular orbit. It's actually an ellipse, right? But so it changes a little bit bigger, a little bit smaller, but it's pretty close to a circle. So there's kind of an average value for R. Okay, so you guys got that? Laws of planetary motion. Okay, all right. Next question is why? Why do these planets move in elliptical orbits? And nobody could figure that out for a long time, right? Then, eventually what happens around 1680-ish, somewhere in there, right? There's this comet that's going to be approaching Earth called Halley's Comet. Now, it wasn't called Halley's Comet at the time, but the scientist at the time, Edmund Halley, was working on this problem. Now, comets have highly elliptical orbits. So comets get really, really, really close to the sun, and they go way out, like past Pluto, right? And it might take them like decades or more to make a complete round trip, right? So highly elliptical orbits comets have, right? And people didn't know that either. It's okay. I know planets are slightly elliptical, comets are largely elliptical, but what's the math that's driving this? And Edmund Halley went to Isaac Newton to ask about this, and Isaac Newton said, "Oh yeah, I figured this out." But and eventually publishes Principia, which the modern day version is your physics textbook and also your calculus textbook because they go hand in hand. Okay, so let's talk about Isaac Newton a little bit. Skip that one, come back to that one. Okay, so Isaac Newton, back in about 1666, give you guys a little history story here. There was an outbreak of plague in London. Also, there was a great fire in London. It was a very, very bad year for London. So anyway, they sent everybody home and said, you know what, it's just a bad year. Everybody go home. Isaac Newton would have been going to college that year, right? And he's sitting in his room and said, hey, I want to take this pandemic time to, I'm just going to figure out how the whole universe works. How about that? So I'm going to do some experiments in my room and figure out like how does everything work? Comes up with laws of motion, does a bunch of work with optics we'll do next semester, figures out like refraction and right? Right. And what eventually made it into Principia many years later after he published this book, because when he originally did these experiments back in 1666, to him it was just a personal curiosity. You know, how does the universe work? And he threw away all his papers. And then many years later, it was, oh, actually, everybody else wants to know how the universe works too. Okay, well, I guess I should publish it. Right? So eventually he comes up with this universal law of gravitation. Now, what he's thinking is he's looking at the moon and he's watching the moon orbit the Earth. Looks outside and he sees an apple fall from a tree. Now, if you ask anybody else back in the day, what makes the moon orbit and what makes the apple fall straight down, what they would have said back in 1665 is, oh, well, there must be two different sets of physical laws. There must be terrestrial laws where everything wants to fall straight down in straight lines. And there must be celestial laws that make everything want to orbit. And that must be the case. And Newton said, actually, I don't think that's the case. I think the moon is attracted to the Earth the same way the apple is attracted to the Earth, but that the moon is moving so fast to the side, has a tangential velocity, that it's falling around the Earth. I think that's actually what's going on. I don't think it's two separate. I don't think they're terrestrial and celestial laws. I think it's one set of physical laws that's driving everything. Okay, so it comes up with the laws of motion, and here's this universal law of gravitation. So okay, so what is the gravitational force between the Earth and an apple, or in this case, between the Earth and the moon? Right? So it comes up with this formula right here. So force, gravitational force, right? The Earth pulling on the moon pulling on the Earth is equal to, right? This force is proportional to each mass. So here's the mass of the Earth, here's the mass of the moon. Multiply those two together, right? Divide by the distance between them squared. Right? Now, guys, when I say the distance between them, guys, look at this distance. Is this the surface to surface distance, or is it the center to center distance? Center to center. You see it like a center mass, okay. Right, so divided by that squared, right? And then to round it all out, I need some kind of constant, a universal gravity constant. So that's capital G. And here's the value for it down here, which I'll show you guys here in a minute where how they figured that out. Okay. You guys see that so far? Right. Now, one question you could have is why divided by a distance squared? Why not just divided by the distance? Right? Why over distance squared? And for that, I'm going to flip back to this slide. This 1 over distance squared shows up a lot of places in physics. It shows up for electricity, shows up for gravity, shows up for light intensity, right? Suppose your eye was like 1 meter away from a candle flame. You light a candle, you back up 1 meter, you're looking at that candle flame, and your pupil is capturing some amount of light. You guys see that? Right? It's like, wow, that's really bright. So you back up further away, and then you back up further away. Because the further away you back up, does the light to your eye appear a little bit dimmer, a little bit dimmer, a little bit dimmer? Suppose you're a mile away. Maybe you can barely see the light at all. Right? Right. So how much of that original light is your eye capturing? Is actually going into your pupil? Well, let's see what's happening to this light cone. You guys see this big old light cone? So 1 meter away, it looks like, okay, it covers this area. If you double that distance to 2 meters away, how much total area does it cover compared to before? How many times the area? 4 times. It's twice as high, but it's also twice as far into the page. You see it? Let's back up to 3 meters away. How many times the original area does that cover? 9 times. You guys see that? So your individual pupil, which is whatever size it is, that didn't change, right? Captures all of the light, then 1/4 of the light, and then 1/9 of the light. You guys see 1 over the distance squared? Right? So this inverse square relationship is actually a consequence of living in a 3 spatial dimension universe. We have like height, length, and width, right? There's up and down, there's forward and backward, and there's right and left. Right? You got it? Right. So, okay, and gravity works the same way. So here's universal gravitation. Right? Okay, you guys okay so far? Right, the other question is, where does this G come from? This 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay, and is that number, here, see if you guys follow this. Is that number an extremely large or an extremely small number? What is that? Small. How'd you know it's small? Because the negative 11 power. Guys, this number is like 0.0000. There's a whole string of zeros before you get to 667. That's a tiny, tiny number, right? Nobody knows why this number is, right? It's just been calculated because of this experiment right here. Here's the first guy to figure this out. Von Jolly in 1880. He sets up this balance. You guys see this bar right here, this balance on this fulcrum, right? I got a green mass here. I got a green mass on the right side. So left side, right side, it's still all balanced. It's all good, right? It's all balanced, right? Then he takes a big old, like 6 tons of lead, this whole big old green ball right here called capital M mass, and rolls it underneath one of the masses. You guys think there's a tiny gravitational force between these two on the left side? Yeah. Do you think that whole scale tips a little bit counterclockwise, it looks like? Yeah. And to restore balance, Von Jelly puts another weight on the right side. Now, I made that red. You guys see this red apple? Right. Chip. Now that's some weight. I put a force here because weight's a force, right? And that force balanced it back out. Now, Von Jelly knows Newton's universal law of gravitation, right? So he knows that this gravitational force is proportional to each mass and inversely proportional to the distance squared. So he divides that over, and he gets this universal gravity constant. And it turns out it doesn't matter what masses he uses or what separation distance he uses. He always gets the same ratio, and it's equal to this number right here. Okay, you guys get that? Okay. Also got this one's fun, but I'm gonna skip past this one a little bit. Right. Orbital speed. Okay, let's go back to the moon orbiting the Earth. Because remember, Newton is the first person in recorded history to make this connection. The moon orbiting the Earth feels the same gravitational pull as the moon pulling down on an apple. Well, it's not the same magnitude, but it's the same effect, right? It's all universal gravitation, right? So how's the moon stay in orbit? For that matter, how do you send a satellite in orbit? You just have to get it going really, really fast, going around. So Newton says, hey, what if the gravitational force is actually acting as the centripetal force? And we have formulas for both of those. Centripetal force, this is straight from your last lab, mv squared on r. Universal gravitation, gmm on r squared, that's from Newton. What if this is acting as that? So they're the same thing, like for the moon. Now, guys, what variable cancels out left and right? The little m mass, right? So whatever is orbiting, like the moon going around the Earth, the mass of the moon cancels. Or you could have any satellite, if it's the mass of a satellite. Turns out the orbital speed does not depend on the mass that's orbiting. Right? It does depend on the mass of the thing that's being orbited. Right? That's the capital M, like the Earth in this case. It's like, okay. So square root gm on r. So if you want to send a satellite into orbit, you have to get going this fast. 6.67 times 10 to the negative 11 times the mass of the Earth. I think is like 5.98 times 10 to the 24. That's kilograms. Divided by the radius of Earth, 6.38 times 10 to the 6 meters. Anyway, put that all together. Take the square root. I think you should get about 8,000 meters per second is what it comes out to. I might have you guys do that someday. But we're getting pretty short on time, so let's hang that up right there.